Okay. So today we're going to start by doing scientific notation. We're going to start really easy with just rewriting stuff in scientific notation. And then we'll go backwards. They'll give us scientific notation and we write the standard form of a number. And y'all, the standard form of a number is how we normally just see the number. Okay, with the commas every 3 digits and all that stuff. And so that's what we're going to start with. And then we're going to graph exponential of functions in section 8.5 and 8.6. So y'all remember scientific notation. You have 1 digit to the left side of the decimal. And you have times 10 to a power. Right? So the digit to the left side has to be a number between 1 and 9. Can't be smaller than 1, which means it can't be a 0. It can't be bigger than 9. It has to take up 1 digit space. Okay? And you can have 10 to a positive exponent or 10 to a negative exponent. If you have 10 to a positive exponent, then that number is bigger than 1. If you have a 10 to a negative exponent, that means that number is smaller than 1. So a decimal 0 point something less than 1. So starting with this number A right here, can somebody read that number to us? What's that number say? Yes, 42,590,000. The decimal is currently right here at the end of that last 0. And to write this number in standard notation, where are we moving the decimal to? Yeah, after the 4, between the 4 and the 2. Now, when you're doing your exponent on your tens, you count how many decimal moves it is. You don't count numbers. You count how many times you move the decimal. So our new decimal is 4.259. So you keep writing the digits until they start being all zeros. And then you do times 10 to a power. And to count the power, you check how many times you move the decimal. So we're moving it 1, 2, 3, 4, 5, 6, 7. Y'all agree? I'll agree at 7. So this number, 42,590,000, is the same thing. It's 4.259 times 10 to the 7th power. Numbers that are larger than 1 have positive exponents. Okay, so the next one is a decimal that is smaller than 1 to start with. And we're going to write it in scientific notation. So where are we moving the decimal to? Between the 4 and the 8. We want 1 digit to the left of the decimal. So that's going to be 4.86 times 10 to a power. Are we going to have 10 to a positive power or 10 to a negative power? A negative exponent because the number started out less than 1. Okay? So then we count how many times we move the decimal. 1, 2, 3, 4. So it's going to be 4.86 times 10 to the what? Negative 4. Any questions about that? Okay, so next we're going to go the other way. They're going to give us scientific notation, and we're going to write the number in standard form, and that's just the regular way we see numbers. So tell me, 9.25 times 10 to the negative 3rd power, is that number going to be bigger or smaller than 1? So we know it's going to be 0 point something, right? So we just count. I just usually write it, and sometimes I'll have to rewrite it. I'll just write 9.25. The decimal's right here. I'm going to move the decimal to the left because it's going to be smaller than 1 3 times. 1, 2, 3. My new decimal goes here. Fill in everywhere with zeros, including in front. And I'm going to rewrite it that don't have my little rainbows on there. And then I'm going to go back and recount because sometimes I miscount. 1, 2, 3. And that's where it goes. Any questions about that? Okay, so the next one says 1.24 times 10 to the 5th power. Is that number bigger or smaller than 1? Bigger. So that's just a little bit bigger. So what we're going to do is write down the decimal and move the decimal to the right 5 times, correct? So 1, 2, 3, 5. My new decimal goes there. I fill in all my brackets with zeros. And y'all, when you write your number in standard form, we use commas. Now, where are we going to put a comma? Right. It's 124,000. So make sure when you write your number in standard form and it needs commas, you put it where it's supposed to go. After the third digit to the left. After every 3 digits. So any questions about doing it backwards? All right, so that is just all old news to us. We've done that for a few years. Next, let's order some in order from least to greatest. I give us 3 numbers. 2 of our numbers are in standard form, and 1 of them is in scientific form. Y'all see that, or scientific notation? So to compare them, it's easier if we have them in the same form. So what do y'all want to do to get them all in the same form? Do you want to make them all standard or all scientific? Well, since I got 2 out of the 3 already standard, it might be easier just to make that middle one standard, right? So what is 7.8 times 10 to the 8th power? I moved the decimal which way, how many times? Right? 1, 2, 3, 4, 5, 6, 7. And a comma goes right here. So that's 78 million. Is that right? Did I do it right? 1, 2, 3, 4, 5, 6, 7. I did. I need one more zero. Sorry about that. 780 million. There we go. Good deal. So when you write them least to greatest, they want them in their original form. So what's the lowest number we got there? 80 million. I use semicolons since we have a lot of commas. What's the next highest? At 103 million. Up, see, comma. And then last is the 7.8 times 10 to the 8. And again, they want you to rewrite them in the form they gave you. That's what your multiple choice questions are going to do to you. Now, if I had 2 of them that were in scientific and 1 in standard, I would probably fix that last one into scientific. Okay? I'd rather change 1 than change 2 or 3. All right. So that's how you order them from least to greatest. Depends on what the directions say. And the bulk of this lesson, where we're probably going to spend, to me, it's more important for Algebra 1, is multiplying and dividing with scientific notation. And this is where we'll get to use our exponent rules, right? Scientific notation has exponents on our tens. So this is why this relates to exponent rules. So when you multiply 2 numbers that are in scientific notation, first thing we're going to do is we're not changing these to standard. Not doing it. We're going to keep it scientific because that's the whole point of this lesson, is to make sure we know how to multiply with scientific notation. So we're going to keep everything scientific. And then what you want to do is you want to group your like things together. So I'm going to get my decimals all together and my tens all together. All right? So I'm going to say 8.5 times 1.7 times 10 squared times 10 to the 6. So I put my decimals together in the front and my tens together in the back. So that's the first thing I do is rearrange. And then after you do that, you take your calculator and you multiply those 2 decimals. And what do we get? 14.45. And we can go ahead and multiply our tens. What do we do when we multiply our tens? Yeah, they're the same base, so we add the exponents. Can I leave that as my answer? No, that answer is not simplified. Why is that answer not simplified? This is too big, isn't it? That's not scientific notation, is it? Why is that not in scientific notation? The number in front has to be between 1 and 9, right? Can't be 0, can't be 10. So I'm going to ignore the 10 to the 8 for half a second. And I'm going to fix this number and make that number scientific. So how do I make 14.45 scientific? Oh, so now that's 1.445. And it's times 10 to the first power since I moved it one time and it was bigger than 1. I'm getting there. I'm ignoring this for a second. I'm changing this number to scientific. I don't just do it in my head. I do it on paper. I didn't make anything confusing.
No, I do not understand.
I ignored the 10 because I want y'all to ignore that for a second. I know y'all are telling me you add it to 9 and you do that. Okay, I get it. I want it on paper for at least your notes. Yes, I want you to look at 14.45 and make that number scientific. That's what we're doing. All right? Y'all understand that that's 1.445 times 10 to the first. Then you drop down your 10 to the 8, and then you can combine your 10s. 1.445 times 10 to the 9. Now, if you can do it in your head and not miss it, it's not going to hurt my feelings. But for my instructional purposes, that's why it happened. Does that make sense? That's why it happened. I ignored the 10, made that number scientific by itself, and then dropped down my 10s. But that's good that y'all know how to do that. All right, this one is all squared. So what do you think we're going to do? What have we been doing? We've been saying parentheses in a square. Yeah, we square everything, don't we? So we're going to square the decimal in the front and square the 10. How do I square the 10? Yeah, it's power of a power, so we multiply. So what's negative 4 times 2? Negative 4 times 2? Negative 8. And y'all can type in 2.4 squared in your calculator for me. What do you get? Is it okay to have a decimal like this for scientific notation? Yes, it is. The 5 is in between 1 and 9. So we're done. We don't have to change any exponents. Is that good? All right, so let's do division. So dividing is pretty much the same way. We're going to do our decimals first. And then we're going to do our tens. So when you do your decimals, you're just going to type in top number divided by bottom number in your calculator. So first we're going to do 2.4 divided by 2.5 and hit enter. And what do we get for that decimal? 0.96. Now how do we get our tens when we divide, do you reckon? You subtract. Now this time you have to do top minus bottom. I know we did big kid gets leftovers the other day, but on scientific notation you have to do top minus bottom. So what is 5 minus negative 4? Positive 9, right? Okay. Now can we leave our answer like this for scientific notation? No. Is our 0.96 too big or too small? So since it's too small when we move the decimal, it's going to be 9.6 times 10 to the negative 1, right? So we're going to do negative 1 for the exponent because it was too small. So if your decimal is too small, you'll have a negative exponent for that one. If it's too big, you'll have a positive. Does that make sense? And then bring down the 10 to the 9th with it. And what is negative 1 plus 9? Positive 8? So 9.6 times 10 to the 8th. Questions? You guys try one of each. Make sure you keep it in scientific and your answers stay scientific. Check it with a neighbor when you're finished, please. All right, what'd y'all do first on number 1? What'd you get when you multiplied 8.5 times 3.7? 31.45, and then you added the tens and got 10 to the what? Fifth. Can you leave your answer like that? Nope, too big. So that's 3.145 times 10 to the first times 10 to the fifth. So your final answer is 3.145 times 10 to the what? 6. Raise your hand if you got that for your final answer on number 1. Any questions? Number 2, what do you do first? Divide. Top divided by bottom. So what's 4.5 divided by 9? 0.5. And what do you get when you subtract your tens? Negative 3 power. Can you leave it like that? Is 0.5 too big or too small? So that's going to be 5.0 or just 5 times 10 to the negative 1 times 10 to the negative 3. So your answer is 5 times 10 to the what? Raise your hand if you got 5 times 10 to the negative 4. Very good. So that's the end of scientific notation. Now we're going to go into graphing exponential functions. And we're just going to combine 8.5 and 8.6 together. Now remember back when we first graphed lines, we started by making a table, right? Remember the XY tables? So that's how we're going to start graphing our exponential functions. Now, y'all, exponents are powers, right? And when we raise a number to a power, it can get really big really fast, especially if we're talking about a graph, okay? So when I'm picking my x values, I want to pick numbers that are close to 0. Okay, you want to do some that are negative and some that are positive. So the ones I would suggest you pick are negative 1, 0, 1, and 2. So I would pick negative 1, 0, 1, and 2. All of these should say y equals something. So it's going to be 2 to the x power. Plug that in, we'll get a y value, and then we'll get an ordered pair. And once we get all ordered pairs, we're going to graph the function. Now we're going to need to know our exponent rules, and they are still on the board from last week. So the first number I'm plugging in for x is what? Negative 1. So 2 to the negative 1 power. How do we evaluate 2 to the negative 1 power? What do we do with negative exponents? It's on the board. Right, so in this case, we'll have to put it in a denominator, right? So when I put it in the denominator, that's going to make 1 over 2 to the first, which is a half, isn't it? Y'all with me? Negative exponents go to the denominator if it's on the numerator. So that y value is a half, so the ordered pair for this one is negative 1, 1 half. And that's really the most difficult one to do the arithmetic with, because the next one is 2 to the 0 power. And anything raised to the 0 power equals what? 1. That's also on the board. So 0, 1. Then I have 2 to the first power. And what is 2 to the first power? 2. Anything to the first power equals itself. 2. And then I have 2 squared. What is 2 squared? So then I have the ordered pair. So does anybody have any questions about how we got the ordered pairs? Now, y'all, we're going to graph these. And we're going to notice when we graph this exponential function, it does not make a straight line. Okay? Exponential functions are not the same as linear functions. They're going to actually make a sort of a curve. So I'm going to say negative 1 up a half. 0, 1. 1, 2. and 2, 4. And when you draw your curve, you're not going to cross the x-axis. And make sure you put arrows on it. Mine's crooked at the bottom of my curve. But that's what the equation y equals 2 to the x power looks like on a graph. Okay? Now, notice it's going to shoot up really quickly. Right? Because after that, 2 to the third power is 8. 2 to the fifth power is 16. 2 to the sixth power, did I skip one? Yeah, 2 to the fourth power is 16. 2 to the fifth power is 32. Right? So exponentials get really tall really fast. Okay? That's why I pick numbers that are really small for my exponents to plug in. Okay? But this is what an exponential function looks like. Notice that the lower it goes, the closer it's going to get to 0, but never cross it. Okay? Closer to the x-axis. So we would call, okay, here's a fancy Algebra 2 word. Okay? The fancy Algebra 2 word for what the x-axis is called to this graph is an asymptote. Asymptote. Yes. I think it's ASSYMPTOTE. The P is silent. Asymptote. Okay? Asymptote. So that means what you do when you have a graph that has an asymptote is it's a line that your graph never crosses. It gets really, really close to it. And so as we use negative exponents, it's going to infinitely get closer and closer and closer to 0, but it's never, ever going to cross it. But it shoots up to an infinity. So if you want to talk about domain and range, domain, remember, is your x's, range is your y values, right? So the domain for this function would be all real numbers, because I could go anywhere left to right, can't I? Okay? But we can't go anywhere up and down. So the range for this function would be y has to be greater than 0. Does that make sense? The range, the y values have to be greater than 0. But the domain would be all real numbers. Let's do a fraction. So go ahead and make your table, and we're probably going to pick the same 4 x's again. -1, 0, 1, 2. Don't get afraid of your x's, because you're going to see lots of them with this stuff. They're really not bad to graph because they don't get really big. And we can estimate where they are on the graph. So when you get your table made, look up at me so I know that we're at the same place. Okay, I see most of your faces. So first thing we're going to do is say 1/2 to the -1 power. And y'all remember that fractions, everything gets the exponent, right? Right? So that's 1 to the -1 over 2 to the -1. And how do you fix negative exponents? You move it to the other side of the fraction, don't you? So we're going to put a 1 to the first power on the bottom and a 2 to the first power on top. And what does 2 over 1 equal? 2. So this one is -1, 2. The next one is the easiest one. What's 1/2 to the 0 power going to equal? 1. As long as it's just one number to the x. If it's like something times something to the x, it would not be. But as long as it's just one number to the x power, it will be. We'll see some in a little bit that it won't be. But when you just have one term to the 0 power, it is. And then what do you think 1/2 to the first power is, y'all? 1/2. and then I have 1/2 squared. How do I do 1/2 squared? 1 squared over 2 squared? Right? What is 1 squared over 2 squared? Huh? 1/4. So everything in the inside gets the outside. So the whole entire fraction. All right, so you graph it. This does not have to be a very tall graph at all because my biggest number I have on there is 2. So I go -1 up 2, 0, 1 on the y-axis, right 1 up 1/2, and then right 2 up 1/4. And it's kind of hard to see this one, but it is a big old curve. It's a little bit wider than the other one we just did. And notice it's going down from left to right. Y'all see that? So if you have a fraction that is smaller than 1, it's going to go down from left to right. That's called a decay. So if it shoots up really quick, it's an exponential growth. If it goes down, it's an exponential decay. And again, we have an asymptote of the x-axis. And so our domain, again, which is all our x values, will be all real numbers. And our range would be y has to be what? Greater than 0. Very good. Let's do one more fraction just for fun. Because I don't want y'all saying y'all don't know how to do them. So that's why we're practicing them. So this is 3/4 to the x power. Same table. I'm going to pick my same x's. Based on the fraction we just graphed, what do you think this graph is going to look like? It's going to go down from left to right, yeah. All right, so first I start with 3/4 to the -1. So what do I do when I raise something to a -1 power, y'all? They both get a 3 to the -1 and a 4 to the -1. Then what do I do? Move them, right? 4 is coming to the top, 3 is going to the bottom. They're both to the first power, so that's just 4/3. 4/3 is the same thing as what number? As a mixed number. 1 and 1/3. So I'll keep that in mind when I graph it. Then I do the 2 easy ones right here. What's 3/4 to the 0 power equal? 1. What's 3/4 to the first power equal? 3/4. And how do I square 3/4? I can multiply it times itself, or I square the 3 and square the 4, right? What is 3 squared? Over 4 squared. 16ths, and that will not reduce, so I'll leave it down to 16. And that's really close to a half, isn't it? A little bit bigger than a half. All right, so let's graph them. These are all positive again. Again, my graph didn't have to be that big. I just did for whatever reason. Y'all told me 4/3 is the same thing as what number? So I'm going to go left 1, go up 1, and go up about 1/3 more. 0, 1. This one looks linear, but we're going to make it not look linear. 3/4 and a half. So we know it's supposed to be a curve. It's just a slow curve. Again, we got that asymptote, so we're not crossing the x-axis. So I know it's hard for that one to look like a curve. Just do your best. So again, this is decreasing from left to right, so it's a decay. What's the domain? All real numbers, we can go either way, left or right. What about my range? X or y is greater than 0, right? No. Let's do one like D and then E, and then we might do just the table for the next one, just so I can show you how to do a decimal. This is 2 times 3 to the x power. So Peyton, this is one like I was talking about a while ago where it's not going to be 0, 1 necessarily. So we're going to make the same table again. -1, 0, 1, 2. 2 times 3 to the x. Let's have some space to work it out. All right, so the first one we'll plug in is -1. So I have 2 times 3 to the -1 power. Now, y'all, the 3 has a negative exponent. So what do I have to do to it? Put it in the denominator. Does the 2 go to a denominator? No, a 2 is going to stay in the numerator. So I have 2 over 3 to the first power, which is what number? 2/3. Does that make sense? You keep the 2 up there because it's got a positive exponent. You move the 3 to the denominator. Does that make sense to everybody? Everybody good? Okay, so that one's 2/3. The one in pairs, -1, 2/3. Then the 0 power makes life easier. However, the answer is not going to be just 1. So what do you think? What is the answer going to be? It's going to be 2 times 1 because the 3 to the 0 power is 1, but you got to multiply it times 2. Does that make sense? So that's the same thing as 2 times 1, which is 2. So 0, 2. And then I have 2 times 3 to the first power. Exponent first. What is 3 to the first power? 3. And so what is 2 times 3? 3. And then last I have 2 times 3 squared. Exponent first. What is 3 squared? What's 3 squared? So that's 2 times 9. What is 2 times 9? Now, don't freak out. I'm not going to graph that one. So if you got one that shoots up to be bigger than 10, don't graph it. Okay? Got it? If one of your numbers turns out to be bigger than 10, don't graph that one. Just graph the other 3. All right? Because I don't want to waste your paper too much. These are all positive. So left 1 up 2/3. 0 up 2. Right 1 up 6. 1, 2, 3, 4, 5, 6. And the rest of them won't fit. Draw your curve. Now this one shoots up really quickly. It's steeper than the very first one we did that looks the same way. Why do you think this one's steeper? What about this equation made it steeper? Yeah, so we already got a number that we're raising to a power, and then we're multiplying it again, right? And multiplying makes numbers bigger, right? Well, multiplying fractions make them smaller, but multiplying times whole numbers make things bigger, right? So that's why that one's so steep. We have not done a negative one yet, so that's where the next one comes in. Oh, domain and range. What's the domain? All real numbers. What's my range? What has to be above zero? Above zero. Y has to be above zero. Very good. So this one has a similar concept. We're raising to a power and we're multiplying it times something. Oopsie. I'm going to use negative 1, 0, 1, 2. Negative 4 times 2 to the x. So first I'm going to plug in my negative 1 for my exponent. So I have negative 4 times 2 to the negative 1. How do I evaluate that? Two to the first on the bottom, so that's negative 4 over 2. Right? And what does negative 4 over 2 simplify to be? Negative 2. Does everybody understand what we're doing with those negative exponents? Anything with a negative exponent goes to a denominator if it's a whole number. So then I have negative 4 times 2 to the 0 power. Exponent first, so what is 2 to the 0 power? 1. So what is negative 4 times 1? Negative 4. And then I have negative 4 times 2 to the first power. Exponent first, what's 2 to the first power? 2. So that's negative 4 times 2, which is 8. And then I do negative 4 times 2 squared. Exponent first, what's 2 squared? So that's negative 4 times 4, which is what? I think we're going to graph that one. It won't even fit on my screen at all. Now, what do you notice about all these y values? They're all negative, right? So this graph is going to look a little different. I'm drawing it bottom heavy. Left 1 down 2. 0 down 4. Right 1 down 8. 5, 6, 7, 8. And the other one I can't graph. So what's going to happen here is going to be a curve. We're still going to get close to the x-axis and never cross it. But notice this one is going down from left to right. That's because we multiplied by a negative number. So y'all, what's the domain of this graph? All real numbers. What about the range? Yeah, this is y is less than 0. Y'all with me? Because everything never crosses the x-axis to get above it. It's all below the x-axis. So y is less than 0. I'm not going to do this decimal problem. I'm going to show you how to do it in your calculator. Because I do want to talk to y'all about growth and decay real quick. When you have a decimal one, just type it in the calculator and get your decimals and estimate where that is on the graph. So to raise it to a negative 1, let me see if I can raise it to a negative 1. So I can hit 2.7. Rooftop. Y'all know where the rooftop button is, don't you? Above the division key. And I'm going to use parentheses and the little negative at the bottom. And I'm going to hit enter. And I get that. And I'm going to check it because I know 2.7 to the negative 1 is the same thing as 1 over 2.7, right? I put it in the denominator. So we'll make sure that's the same thing. It is. So it doesn't matter if you raise it to the -1 if you do, you actually do the rooftop, or if you do 1 divided by that number. Does that make sense? Because negative exponents go at the bottom. And then obviously it's to the 0 power, it's going to be 1. To the first power, it's going to be 2.7. And then you can do 2.7 squared. And there's the other one. And then you can just estimate like we do decimals when you do your graph. Does that make sense? Okay. Let's talk about growth and decay. You don't have to write this problem, but I do want you to write the exponential growth model and the formula. But you don't have to write that big paragraph. I like talking about this stuff because I like thinking about ways I can save money, how I can invest money. I don't have a lot of money. I'm a teacher, but I like to look at ways that I can put some money back and where will it grow, will it mature, even with me not touching it. So, me and my husband are nerds. We know that, but we're always looking on computers for banks and stuff like that that have good ways for us if we have some money that we don't need and it's sitting in savings and we're not going to use it for the next 5 years. We like to look to see, okay, what can I do with this money so maybe it can earn me something sitting somewhere else, right? So anytime, I'm not a big gambler, so I don't really do the stock market, but anytime I can look for some kind of ways that if I can find a good savings account somewhere, which that hasn't happened lately, and or a CD or something that I can gain interest on my money, that's something we like to do. Now, granted, we don't have just tons that we can put away, but any little bit helps. Because hopefully I won't work forever, and I'll have to take care of myself when I'm old, right? So, grown-up things to think about. So what we have for the exponential growth model is the formula y equals 1 plus r to the t power. Now let's just talk about what those variables represent for a second. Your A term is your initial investment. What do you think that means? That's how much you start with. Your initial amount, initial, like your initials in your name is the beginning letter, right? That's how much you have at the beginning or how much you're investing. Okay, so A is your initial amount. R is the rate, which is the percentage converted to a decimal. And T, what do you think T is? It's time. It's how long it's sitting there. Okay, it's usually done in years. So it says you put $250 into a savings account that earns 4% annual interest compounded yearly. If you leave it alone, how much will the investment be worth in 5 years? 4% is pretty good. Okay, my silly little bank account is only getting like 0.5% now. It's terrible. Okay, so what we're going to do is we're going to plug everything into that model. So we're going to say y equals, what's our initial amount? 250 times 1 plus, because we're gaining money. Now, what's 4% as a decimal? 0.04, right? We move the decimal twice for a percentage because it's out of 100. Okay. To the t power. Now, how long are we leaving it there? 5 years. So then we add inside our parentheses. 1 plus 0.04 is just 1.04, isn't it? And then we're going to do our calculator. Remember, exponent comes before multiplication, so we're going to do 1.04 to the 5th, and then multiply that number times 150. So 1.04. Rooftop, 5, enter. And then I'm going to hit times 250. How much am I getting? Oh yeah, we round money like we do. $304.16. So if I just stick that money in there and don't touch it, after 5 years, it gains me about $54. Right? Not bad. Y'all understand how we plug that in? How everything went? The only thing funky is changing your percent to a decimal. Okay? And then you do order of operations. All right, then we have the decay model, which is the exact same thing, except for 1 plus R, it's 1 minus R. Instead of 1 plus R, it's 1 minus R for a decay. A still talks about the initial amount or the starting amount. R is still your rate, which is a percentage converted to a decimal. Your T is still time. Only difference for decay is a minus because you're losing something. It's going down. It's decreasing. So gross, you're gaining, it's a plus. Growth is gaining, it's a plus. Decay, you're losing, it's subtraction. Makes sense. All right, so they're going to give you a formula, and you tell me if it's a growth or a decay, and I'm going to show you the trick to determine that. And then you got to find what percentage the increase or decrease was. Okay? So the trick to knowing if it's a growth or decay is look in the parentheses. If it's more than 1, it's a growth. If it's less than 1, it's a decay. That's it. So is this number more than or less than 1? Less than, so it's a what? Decay. You just look there. If it's more than 1, it's growth. Less than 1, it's decay. How do you think I can find the percentage of how much it decreased?
See how much it takes to get
Exactly. So if I take that number and subtract it from 1, so 1 minus, sorry, I can't hold my calculator in my, 1 minus 0.985, hit enter, I get 0.15, 0.15. And how do I convert that to a percent? Move the decimal how many times? How many? 2. 1, 2. It's a 1.5% decrease. So you find the difference in that number and 1, and then move the decimal 2 spaces. That's it. Just threw my pen. So let's do one more. They're going to give me the model, which is the equation. I completely just broke my pen just then. I have a backup. When I just dropped it, it completely killed it. Thank goodness that some pens work on this different tablet PCs. Okay. So this one. Do you think this one is a growth or a decay? How do you know? Because that number in parentheses is bigger than 1, so it's a growth. How do you think we're going to find the percent of increase or decrease? Find the difference. This is from 1. So obviously it's bigger than 1, so you're going to do it backwards. 1.25 minus 1. And what do we get? 1.25. And then how do I find the percent of change? 1, 2. How many percent? 25% increase. All right. So that is the end of our lesson for today.